Okay. Hari ni kita akan go to hopefully sempat lah. So basically under this topic, right, we're going to go to the effect of dislocation, how dislocations affect the materials, the properties or strength. We're going to go to a couple of strategies to increase the material strength. Okay. So basically, last time, if you recap from the chapter 3 or topic, you have whether you have a shear or you have a tension, then the components may experience screw and edge dislocation. Okay, so this dislocation technically depends on the material crystal structure as well. So technically, talking about dislocation, if you don't have any edge or screw dislocations, then there will be no deformations. Okay, kalau tak ada screw or tak ada edge dislocation tu, dia takkan ada deformation. So practically, you go to last time dalam topik 3 itu, is to explain the mechanism how dislocation take place in the perspective of screw dislocations and also in the perspective of edge dislocations. Okay, so dengan kata lain, if there is no edge dislocation, if there is no screw dislocation, means that there will be no plastic deformation. Okay, plastic deformation is permanent changes lah. Okay, so this is just a recap. Right, so basically dislocation is depend on the atomic packing factor, which is you have learned this in the topic 2. Okay, you dah belajar dalam topik 2 yang lepas. You dah belajar macam mana nak kira atomic packing factor. How does the atomic packing factor affect the slip of the material? Okay, ada ni tu. Okay. Okay, alright. So ni just recap. So atomic packing factor and the slip itself, you belajar itu. For the slip to occur, they need to have a plane. They need to have a directions. So bila you ada plane, you ada directions, combinations of both, you're going to get a slip system. And slip system sebenarnya is defines the ability of the material to be deformed ataupun how easy the atoms can move. So that's the idea. That's the concept. Yeah? So kalau you tengok deformations mechanism, just a recap a bit. Deformation inside the material on the physical properties or physical structures, as we can see in two conditions. One is under elastic condition, second is under plastic conditions. So kalau elastic condition is that whatever load that you apply, okay, whatever load that you apply, as long as it is below the yield stress, is at this point, then the material will experience elastic deformations. Okay, so if you bend certain material, then if you remove the load, as long as the load is less than yield, it tend to return to original positions, original structures and everything. But for plastic deformation, it's different. The moment the load that you apply is exceeded the yield strength, the material start to, it cannot return to original structures or properties. It means that it behaves like plastic deformations. Okay, so under plastic deformation, we're going to go through two characteristics. One is brittle fracture, and second is ductile fracture, or ductile deformations or brittle deformation. Now let's have a look into this stress and strain curve. To expect you guys too familiar with this kind of diagrams. So if you label the stress and strain curve, you have two regions there. One region fall under elastic region, and second is fall under plastic region. Okay, so whatever load you apply in this region, elastic region, the structure can return to original. Different with plastic region. The plastic region, the material tend to elongate Up to certain point, it's going to be failed. So let's have a look into the first conditions. Okay, under elastic conditions. All right. For example, like this is point number 1. You apply initial conditions. We view in the perspective of how atoms behave inside the material. Right. The changes of the positions of the atoms inside the solid material, it cannot be seen by the naked eyes. So that's why you need to understand the reasons why it deformed because of this characteristic or because of this behavior. All right, let's have a look into the first condition under elastic deformations. Right, at this point, at point number 1 here, you can see all the atoms are in their equilibrium conditions, where there will be no force or applied. But somehow you apply loading, maybe somewhere below the yield point. Let's say we stop at point number 2. Right, then you can see the atomic arrangements now start to distort a bit. Right, dia tak putus, dia tak pecah, dia distort a bit. Right, so this one, atomic bonding, in terms of atomic bonding, they might experience a bit of stretch, but then they do not break. Okay, but then when you remove the load, so the first condition is below the yield point, you remove the load. So the moment you remove the load, it returns to original position, which we assume as point number 3. So your structure is now back to the original position. Right, they restore to the original position. There will be no changes in terms of lattice size, length, and everything. So that technically explains on the elastic deformation. Now we move on to the second criteria. Okay, or second deformation is plastic. For the plastic, let's start with the ductile deformation first. If you look into this diagram, if it is elongates, we have elongation, changes in terms of strains here. So meaning that it experiences ductile deformation. But somehow, if let's say the component of material experience a very small deformation, like a ceramics material, the moment that you put the tensions on the ceramic, it breaks. The ceramic, they do not elongate. So those are the things. Okay, let's have a look into the first aspect first. We look into the ductile characteristic first. Right, so the first criteria, you apply load at number 1. Number 2, same as before this. I'm not going to explain number 1, number 2, the same changes as well. But the moment, let's say at point 3. If you look at point 3 here, the moment the load is succeeding the yield stress, right, the yield stress technically explains it is between the transitions from elastic to plastic. So the moment that the load you apply to the yield stress, then you can see you start to introduce extra half planes. Remember, it could be edge dislocation, or it could be screw dislocation, depending type of external loading that you apply. If you apply shear force, then you will have a screw dislocation there. But since the graph is under tension conditions, so we assume you have extra half planes there, which is identical or similar to edge dislocations. Right. So what happened now? Right, at point number 3, you can see a split plane start to form. Right, you will see the changes in terms of lattice size expansion. Some of them are stretched, right? Some of them start to stretch, repositionings, and everything there. At point number 3, right? So if you look into the physical structure, in that you can see the changes in terms of shape, the changes in terms of dimensions. This is point number 3. But you extend the loads a bit. Extend the loads a bit, the material to prolong, and up to the point that they cannot stretch anymore. Up to the point that the lattice itself, it cannot stretch anymore. So you start to break the lattice fracture. Okay? So it cannot accommodate dislocations. Then you will have a crack. Then towards the end of the day, the component will fracture. So this is what happens. Okay, so this is we are discussing on the perspective lattice arrangement, but somehow if you look into this one is isometric, this one is cross-section view. This diagram, this is cross-section view. You view on this direction. So you nampak the arrangements of the atoms it's back. It's making atoms easier to move. Okay? Because at the end of the day, this location define how easy atoms to move. A lot of atoms it's easier to move, means that the strength of material is poor. Right? So for FCC material, you have three type of forms, densest plane. Why you have 4-1-1-1? Because we are looking into various directions and symmetry. And sleep direction, same goes as well. You have this direction, this direction, this direction as well. And then sleep system is calculated by number of sleep plane time with sleep direction. We have total of 12 sleep system. So maksudnya for FCC material, the material can be deformed into 12 sleep direction. So that's other thing. So let's have a look into the previous as well, just a big recap. This is on the topic 3 and also topic 2. So if you look into FCC material, they have 4 dense planes and also they have 3 sleep directions sitting on the densest atomic positions of arrangement. But somehow, if you look into BCC as well, they have a sleep system. They have 6 plane, densest planes, and also 2 densest directions. Okay, total is actually 6 times 2, you get a 12 sleep system. It's similar to FCC. But somehow, why FCC for this case is more ductile compared to BCC. It's softer than BCC. Right? So to explain this, we view in the perspective of the packing factor itself. We call it a closed pack structure. So if view in terms of FCC, most of the atoms are touching each other. It'll be much more easier for the atom to move. Lesser energy to be break to overcome for the atoms to move. Compared to BCC, you have more gaps here. So means that more energy required for the material or for the solid structure to deform or to experience plastic deformation for this location. As you see this slice, you only have one densest plane down there, and then you have a 3 directions, 1, 2, and also 3. So total sleep system in SCP is about 3. So it's the lowest when you compare with FCC and BCC. And this technically making SCP material or metal having HCP, the hexagonal closed pack, is stronger compared to FCC and also BCC. Alright. There's supposed to be another slide, but somehow. Okay, only one slide. So assuming the first characteristic here, the next plastic deformation characteristic, you have brittle and also you have ductile. For brittle behavior, by the way, you assuming you apply the loading, point number 1, point number 2 is similar behavior. But up to this point, for brittle, the material technically ruptures straight away. Right? They do not have the characteristic of the lattice to expand or to stretch. So they are just rupture. So this is what happens on the brittle regions. Yeah? Right. So these are the sleep systems. Another dislocation characteristic other than sleep is known to be twinning. Okay, so we have go through because most typical or common deformations in material is that it's based on the sleep directions. But somehow there will be another case that the material will experience twinning characteristics. Right? For example, twinning basically is like caused by the shear force is mirror or mimic to the shear dislocation, but it is not shear. The difference between shear dislocation and also the twinning is that, as the name itself, so whatever deformations happens on the material is mirrored to the other side. That's why we call it a twinning. For example, like this microstructure, in the perspective of microstructures, whatever deformations occur on this side is similar to this side. That's why they call it a twinning. Okay, if you look into the perspective of BCC, sometimes BCC experience twinning as well. For example, like this, BCC twinning occurs on the 112 planes with one direction. So if you have your cubic thing, then you can see this is actually how it goes through. Right? It's like a symmetrical, it's like a twin or mirror. Yeah. All right. Then this one is comparison. Comparison between twinning and also slip. So talking about slips, they involve the line defect. They involve a line defect. So you have two types there, whether it is edge dislocations or screw dislocations. So twinning normally they occurs on the surface defect, which is at the grain boundaries. Berlaku dekat grain boundaries. So slip most of the time FCC, BCC material, like they will experience slip, whereas SCP with limited slip deformation or slip system occurs on the ACP. Okay. So basically, if you in the perspective of the stress, slip require less stress, but somehow for twinning is double up, right? Because you are having mirror changes. Yeah? So one side and other side need more stresses to experience twinning characteristics. Yeah. So twinning is what else I can say. So twinning slip, yeah. Slip normally occurs in several milliseconds, right? Is slow process. But for twinning occur in a few microseconds. It's a very rapid and fast process. So these are among the comparisons between slip and also the twinning. You can select any other 2 or 3 points or 2 comparisons. I think it's enough between the slips and also twinning comparison. Right, let's have a look. Just a bit overview where the twinning technically being used. Right, twinning, the process basically tweak. Right, for example, like twinning induce plasticity. They use in the car or any automotive body. One part of it is experience twinning plastic deformation. So if you look into the properties of the twinning material, whatever components or metal experience twinning, they can sustain higher loading conditions compared to the standard steel material. The blue line refer to the standard or it's just a standard steel. So you can see a lot of changes between tweed material and also the standard material. And this one is excluded the slip. Slip tak termasuk dalam press grain curve pattern. Alright, so we are done on the dislocation. Now we are moving on to the second topic of topic 4. In topic 4, we have 3 topics. We have dislocation, we have strengthening mechanisms, and the other one is a bit on the heat transformation. Okay, and the strengthening mechanisms. The strengthening mechanism is a process that you wanted to restrict. You wanted to inhibit the movement of the atoms. Atoms are moved, of course. The moment is moved, technically indicate the material is softer. Although the strength increases, but in terms of elongations now become shorter. Okay, so this is the functions of the dislocations. Of course, they can improve the strength, but somehow in terms of other aspect, for example, like ability to elongate, ability to be shaped multiple times has been restricted. Okay, so that's dislocations. The obstacle to dislocations, a couple of them you can work with. You have a solid atoms, you have a substitutional, you have interstitial, you have a grain boundary. So we have discussed in the chapter 3, type of the defect. Dislocations, interactions, sometimes we call it a cold working. Phase changes by the heat treatment as well. We're going to review it today. Precipitates, we're going to review it today. And the basic thing about the material, how we define the strength, always come from the bonding. It will be a lower one. Okay, but somehow for the bonding, not much you can do because it could be natural state of the material itself. Okay, for example, like a metal. So of course, it's a metallic bonding. It's a metallic bonding. So you cannot change metallic bonding to another metallic prime 1 or prime 2 bonding. So, but somehow the basic thing is that the material approximations of the strength lies on this type of bonding. Okay, so that is basic of the material science. Now let's have a look into the first strategies. Out of many, we're going to discuss 4 only. So you guys need to know the at least minimum of 2 strategies. Okay, because either in final exam or in test 2 or in test 1, final exam or in test 2 or test 1. If you are lucky, the questions may look like a general. Or explains example of strengthening mechanism to improve the strength of the metals. Then you can mention 24 of them. But if you're not lucky, then we basically we highlighted based on the precipitation strengthening mechanism process. Explain the step by step of how to improve the strength of aluminum. Okay, the first question, if you recall the first question, is a bit general. Katanya you random sahaja. So mana proses nak kuatkan bahan tu? You ada 4 strategies. You remember one, then you're lucky. Tiba-tiba tikam tu masuk. If you're not lucky, is that we perhaps purposely put one of the strengthening mechanism. For example, like precipitation. Letak dah terus kat situ precipitation. Kalau you tak ingat, then you are gone directly to this question. Okay, so biasanya akan ada lah. So kalau kita recap back, somewhere in my previous slide, I'm not sure which is which. This one? This one? Perhaps this one. Oh yeah, this one. See? Here is another example. Explain 2 example mechanical applications where dislocations play important role. It's identical with chapter 4. Sama juga lah. Saya tak ada ni, tapi tak perlu. Nanti next week punya class, I'm going to put couple of questions from the past year, and then test 1 and final exam. So you guys can review this. What else? This one. Okay. The first strategy is to strengthen the materials or metal specifically is by reducing the grain size. Okay, so grain size means that you have more grain boundaries. Right, so grain boundaries, as I mentioned to you before this, is part of the surface effect. Right, your boundaries is a wall. So it's a barrier. So it means that the finer the grain size or the smaller the grain size, the more barriers that you have, the more grain boundaries. So these barriers and also wall technically provide a strength to prevent dislocation from happening. Right? Smaller grain size, basically more barriers, and would be much more difficult for the atom to move. And this behavior technically obey the Hall-Patch equations. What does Hall-Patch equation stand for? If you look into the diagram, the y-axis is yield strength. We're talking about yield strength here. Your x-axis is the size of the grain. Right, this one, if you look at this, 10 minus to the power of 1, 0.1. So moving toward right side, you have 5 times 10 to the power of minus 3, which is 0.005. Okay, so this is changes. So means that this is larger size. Ini grain besar. And this one moving from left to right, you can see reductions into grains. So this behavior you can see when you have a component made from 70% of copper and 30% of zinc. Right, so you have this behavior obey from Hall-Patch equations. That means that the smaller the size, the higher the strength wave. Okay. So do you need to remember these Hall-Patch equations? No need for you to remember. Okay, tak perlu ingat, tak perlu hafal. Dah 10 tahun. Starting 2016 sampailah 2025, there will be none of the questions technically ask you to derive the Hall-Patch equation or to use the Hall-Patch equation to solve the grain characteristic. It's just for your information. What you need to do is that you need to understand what does the reduced grain size mean, what will be the features looks like, how the grain features will look like. Right? What does it mean by the grain boundary? How the grain size correlate with the grain boundaries? That'll be all. Now you're going to look into the second strategies. Simple. Right? You have the 4 strategies. Grain size paling senang. The second strategy is by the solid solutions. The solid solution we have discussed in the topic 3 under diffusions. Okay. We have discussed in the topic 3 as well. So technically, solid diffusion meaning that you add impurity or you add another material inside the base material or parent material. That's why they call it alloying. Solid solution also known to be alloying or alloy process. So the moment that you add, for example, like smaller atoms, your lattice structure now is having a localized stress. Could be at point A and point B. In case your atoms are smaller compared to your base material. If you look into the top diagram, inilah contohnya. So what happens is that if you look into this structure, then you can expect this plane changes in terms of planes directions. Used to be straight. Right? Kalau you dapat pure material, used to be straight. It's much more easier for the atom to slip. Somehow your planes now you have a bit distorted, right? So this technically make the atom slightly difficult to move. So and because of this, you can increase the strength of material. The same goes, the same phenomenon you're going to see if you add the impurity or additive material is slightly larger compared to base material or parent material. When I say about base material or parent material, means that it is majority percentage inside those metals. Okay. So what happens is that if you add larger atom, then you're going to create a localized stress at the edge of the lattice. So technically, this will oppose or prevent the atom from the slips. So this is the behavior. How additions of alloying or impurity or additive material improve the strength of the metal. All right. So these are the real applications. We looked into the practical applications. For example, like you have nickel and copper, right? Nickel and copper. supposed to be nickel and copper. Copper here. Okay, so it means that at this point you have 100% of the copper. The way that we read this, 0, 50% refer to percentage of the nickel. So remember, the combinations of copper and nickel is always 100%. So if you read like this, it means that increasing the number of copper. Okay. At this point, 0% of the copper, 0% of the nickel, which is 100% of the copper, you can see the strength is low. Okay, it could be 210, 220 megapascal only, the ultimate tensile strength. But the moment you increase the percent of the nickel inside the copper, you can see the strength now start to increase. For example, like you add 20% of the nickel inside copper. So it means that you have now 80% of the copper and 20% of the nickel. Okay, total must be 100%. It cannot exceed 100%. Now, if you look at these points, the strength now has been increased from 210 or 20 become 350. This additions of 20% of copper. Okay, so same goes with this. If you look into the perspective yield strength, okay, this is ultimate tensile strength. This is yield strength. The strength is the maximum load that you can apply before you break. The yield strength is the load that you can apply, right? It's not the minimum. It's the maximum. I can say it's maximum. It's not. It's the maximum load that you can apply before materials start to deform. That one is yield strength. For the design aspect, because you guys are an engineer, so we are talking about yield strength. Always go with the yield, because once the component is compromised, or deformed, the integrity now has been compromised. So sama juga dengan yield strength. Increase the percentage of the nickels, right? Then you can expect the strength of the copper increases. Why 50%? Because alloy is about 50-50. Parent material must be larger than base material, larger than alloy material. So bila dia dah lebih daripada, let's say lah, 51 of the nickel. So now we are saying that strengthening in nickel, not strengthening in copper. Okay. So the next strategies, we still got a couple of time more. The next strategies is precipitations. Precipitation, basically you have a dispersed particle. So like this one, we look into the diagram lah, senang sikit nak faham. So assuming you have a precipitate in this slide view, if you have a plane, right? If you have planes, the presence of the precipitates, technically, well, we can say that more energy, more stress, more load is required to overcome the precipitates. This one is top view. If you view from the tops. Okay, so this behavior is known as Frank rate behavior. So saya tak boleh lah kat sini. On the next slide ada. But then if you look into the microstructure itself, how it's going to be looks like for the precipitation, assuming aluminum as a matrix, your silicon is a precipitate. So you're going to see how this one looks like. You can nampak. So kalau you ada crack here forming at this, or deformations, every single SiC particle technically will block the dislocation. Why? Because aluminum is soft material, but SiC is a ceramic material. It's a hard material. So more loads, more force required for you to break this kind of silicon carbide particle or ceramic material. Okay, right. The real application, for example, like a Boeing, if any one of you experience travel with the Boeing or Airbus, and you can see the bodies itself is made by the aluminum alloy, additions of the silicon carbide. And this is how the mill looks like. You're not going to see on the surface. You need to prepare, do sample preparation, polishing, do the etching, then you can see this structure. So the strength of the body, aircraft structure technically has been strengthened by additions of this dispersed particle or precipitate. Okay, just imagine the whole structure of the aircraft or Boeing is made by the pure 100% of aluminium. Aluminium is soft. For example, like aluminium sheet. Aluminium sheet. Pembungkus makanan lah, packaging, aluminium packaging. It's soft material. That one is a pure aluminium. We're talking about pure aluminium. So above the sky, you can see the pressures are actually very low. The turbulence are massive there. So you can expect this wing, it can bend up to this point. So if your structure is now made by the aluminum, well, basically we can say goodbye to all of the passenger. Right? So it's going to be crash lah. The structure is going to be crashed. So that is actually how we strengthen materials. Okay. Under the precipitation is a bit longer compared to other strategies. So they have 3 stages. You guys need to remember this. So, and all the steps or stages, you need to run it sequentially. Always start with the solution treatment, the first step. Also followed by the quenching. And next is aging. So you tak boleh lepas solution treatment, you not jump to aging and then go back to the quenching. No, it's not going to work in that way. So assuming this is the phase diagrams, part of the phase diagrams. So phase diagram ni besar lah. Yang saya tunjuk ni pendek je, up to 10%, 20% something. So in the solution treatment, what happen is that you heat the specimen or samples. You punya y-axis, you punya temperature, 20 degrees C, room temperature. So you heat, right? Because P1 as a stage number 1, solution treatment, sometimes they call it solutions anizing. You heat until you get a single phase. So dekat point K plus A ni, you dapat 2 phase kan. But point number K ni adalah single phase. So sebab tu, the first step dalam precipitation adalah you need to heat the alloy until you get one solid phase sahaja. Okay. And then you can accede to the eutectic temperature. Eutectic temperature is a new terminology. So you're going to see it a lot in the chapter 6 and chapter 7. Eutectic is a phase transformation from the solid to the liquid. So dengan kata lain, bila you buat solution treatment, tak perlu sampai dia cair. The aim of the solution treatment is that you wanted to get a single phase only. So, for example, like you have a K plus A phase, ataupun saya simbolkan A plus B phase, because you have 2 materials here, aluminium and copper. Right? So, you're going to get 100% single phase only. Okay, so single phase only. This is the solid solution. The next step is that what you need to do is quenching. So you dekat sini dah sampai dapat single phase. Then you do a rapid quenching. Rapid quenching, for example, like if you heat the sample at this point, 600 degrees C, you take out the sample from the furnace, you put inside the water. It's a rapid cooling, the rapid temperature changes from 600 to 25 degrees C. Bukannya you ambil tu, you letak atas meja, you ambil tu letak mana-mana. That one is a slow cooling process. Tapi you letak dalam air. That one is known to be quenching. It is non-equilibrium cooling process. So what happen is that, saya lupa nak tunjuk reaction tadi. So untuk PY ni lah contohnya, warna hitam B, warna putih ni adalah A. So bila you heat sampai A, you akan dapat putih saja, which is A lah. So you apply quenching. Quenching is a rapid process. So diffusions are slow because this one is fast heating. Right? So dia tak sempat nak form a black precipitate ni, they maintain the structure. So the target is that you wanted to maintain the single phase yang dapat satu fasa je kat sini. So sampai dekat room temperature ni. That is the quenching process. Okay. The next process that technically determine the properties of the material is the aging. So you ada aging kat sini. So aging ni you apply a slightly lower temperature compared to the solutionizings. First you heat at 600, but aging is lower than that, 200, 150 for a certain amount of time. Then you will form a precipitate. Precipitate ni come from where? Come from B. Right? So B start to grow again and become a precipitate, become a fine precipitate. This ones technically provide you a stronger properties. How? So this basically explain this behavior. Precipitate yang dapat directly, the structure of precipitate ni is directly proportional with time. If you prolong the aging process a longer duration, your precipitate now start to grow into a bigger. So the process is known as coarsening. Jadi besar coarsening macam ni. Coarsening ni tak bagus lah. Okay, so that is aging. So this one is more or less like to explain to you, right, the effect of the aging. If you look into the first diagrams here, okay, how the aging affect the tensile strength and also affect the ductility. So ductility is opposite properties of the tensile strength. Okay, so kalau you tengok kat sini, for example, like aging, different temperatures, you have a different temperatures ya, daripada 121 sampai to 216. The higher the temperatures is, like for example kat sini, you will get a precipitate, fine precipitate shortly, cepat. It's 1 minute you get directly. So you prolong the aging time, for example, like 1 hour, the precipitate become longer, become bigger. So if you look into the strength, basically larger precipitate reduce the strength of material. But somehow, if you put two lower temperature, for example, like 100 degrees C, it takes about 1 month inside the furnace for you to get the maximum properties of the tensile. Okay, so that's why under aging characteristic for this case, you need to know the temperature that you're working with, and you also need the time. That is aging. And last but not least, before we stop, the last strategies, which is strategies number 4, the cold working. Okay, cold working, also known as flame hardening, it's a quick process. You have many processes there. You can be forging, you can be rolling, extrusions, you are the drawing. So whatever process, cold working that you apply with, you can expect the changes in terms of physical dimensions, shapes, and everything. And if you look inside the component itself, you can see the changes of the grains. Right now is actually you have equate grains. After you apply the cold working process, your grains now start to elongate. So if you are required to draw the microstructure, this is how the microstructure should be drawn with. Right? Sepatutnya bentuk macam tu. And the strength of material, by the way, is depend on percentage of the cold working. So if you look into this equation, you need to remember this equation. It's a changes of area. Area initial minus area after you apply the cold working divided by initial area times by 100%. So it must be in the area units. So you cannot put high, you cannot put length. You can try, but then you will get different answers. Okay? So the higher percentage of cold work will increase the strength, of course. So what happens inside the cold work is that if we look into the micro scale level, you will see a lot of dislocations, right? So we call it as a dislocation density. The higher percentage of the cold work scene, you will get more dislocation density. So meaning that it will be much difficult for the atoms to move. Okay, so these dislocations technically overlap to each other. So they entangle to each other so that it makes the atom difficult to move. And this behavior is actually known as Planck rate. Planck rate ni kat mana? Which is shown in this diagram. Ini adalah Planck rate behavior. So cuma nanti saya tambah lah kat sini. Okay, so let's look into the practical application. For example, like you have a 0% of cold work. You're talking about stress strain curve now. Right, initial material, any material, you name it, aluminum perhaps, the green color, percentage of the cold work. Then you apply the drawing process, 4% of it. That's mean 4%. Your bit process ni about 4%. Changes is about 4%. Why changes? Because if you look into this equation, area final, area initial minus area final or reduction divided by area initial. So changes. So lagi besar you punya percentage of cold work, then you can expect the strength now is increases. Ini lagi tinggi. The blue line is higher than green lines. But at the same time, your strain characteristic now has to be reduced. So reduce. Okay. So kalau word ni bagus lah. Dia akan improve the strength if you're talking about strength. Okay, we're going to improve the yield strength, tensile strength, ductility of course is going to be reduced. So ductility tu apa? Is measured by unit of strains. So, lagi pendek lah maksudnya. This equation you guys need to remember with. For example, like these calculations, right? This last slide before we end. Cold working analysis. What is the tensile strength of ductility after the cold work given to you? Initial diameter of the cylinder is about 15.2. Then you apply the cold work. Right, you get diameter of the rod itself is about 12.2 mm. So remember the percentage of the cold work, how it's being calculated. So you know the area for the cylinder is that. Okay. So you just use the equations here. You know the radius changes. Then you get a 35.6%. So it looks into the 35.6% of the cold work act axis, by the way. Then you know the yield strength is about 3300 MPa for the copper. Then you can do the same thing for the tensile strength again. The same percentage of the cold work, 35.6. Then you can get 340 for the tensile strength. Okay, and the ductility, of course, has been reduced. Right, it's been reduced to 7%. Okay, itu kalau tengok percentage of cold work. Kalau you buat 0, then ductility is high. The strength is low. The yield strength is low as well. But then if you increase the cold working percent, although it's about 30%, then you can see major changes in terms of the strength. So yeah, that will be all for today's sessions. We're going to continue the rest of the topic 4 next week, Monday. If there is no question or you have any, you can put on the WhatsApp as well. I'm not going to take the attendance. Your attendance will be directly captured on the from the team itself. So you can have a look on the chat area, previous attendance. Your attendance will be taken directly from there. So thank you, everyone. So that should be all for today. Taking a bit longer today. We adjourn our class with Tasbih Khafarah and Sasiratu. Thank you, everyone. All right.